but for other reasons has not. And it's only these few little white regions that are actually the nuclear active material. And I would propose that material that gives lots of heat will have many of these little regions on it, and that which gives very little heat will have only a few of those regions on it. And therefore, the important thing is to know about those regions, not about the rest of the sample, if you're going to develop a theory or an insight as to what's going on to make the energy. Thank you very much.
Thank you very much, Dr. Thomas, and now the paper is open to discussion.
Does the crack volume contribute to the electrical resistance of the sample?
I can't tell that because I don't measure the resistance. But the cracks, most of the cracks are so small that it's really hard to resolve them with a microscope. Occasionally, visible cracks do form, and those would obviously have a big effect. But I don't know the answer to that.
Other questions? Translator.
Do you see your open circuit voltage change with different cathode geometries or additives or anything like that?
Oh, yes. Yeah, it's quite sensitive to
It should be.
additives, what one does to the sample. I mean, you can make substantial changes in it, but now most of those changes are generally to make it lower. It is quite difficult to make it higher. And that's, of course, the challenge that is presented to us in this field. You have to make it higher for the nuclear active material to be formed. That's the tough one.
Okay. Proceed.
Can you explain some reason you consider the active region is local and small? Can you explain some reason you concluded that the active region is small and local?
Well, I think there's two reasons or two bases for that conclusion. One is simple logic based upon the manner in which these things behave, their irreproducibility and all the rest of it. Also the fact that palladium deuteride is not normally nuclear active. I mean, we have more samples that are dead than we have that are alive. So it has to be something that you have to convert to, something you have to make. So I would suppose that which you have to make would be a rare occurrence because it is so difficult to find the conditions in a piece to make it. And when you take a piece of palladium and take it out of a bigger sheet, you're not necessarily just cutting at the boundaries of a piece that works. It's a random thing. So you would expect to see random characteristics on the surface that are conducive to the production of this nuclear active state. So just on that logical basis. Going a little further, there is evidence in my data that there is an inhomogeneity to the surface. Now, I can't see it on a fine enough scale to know that it is so small an area, but that's my gut feeling that it is. But there is an inhomogeneity there.
Okay, please. Short question, please.
Ed, do you have any suggestions regarding the alloying of palladium as a result of your work? In other words, why would alloying generally likely help, or would you have any suggestions?
Well, I think alloying has an effect in both directions. Clearly, the boron is detrimental, marginally detrimental. It's not overwhelmingly so, at least at the 500 parts per million level, but it is detrimental, and I'm absolutely certain that other alloys could be beneficial. I have at my disposal now a variety of alloys provided by Tom Plater that I'm going to explore in this context to see if there is some benefit. But right now, I only have 90 pieces of palladium that are not alloys, except for with respect to boron. If any of you have material that you would like to have looked at in this context,
Sanchez has questions.
I'm wondering about the meaning of what do you mean by a new phase, a possible new phase at the surface? And we're speaking in crystallographic sense. What kind of new phase? Can you explain a little bit more about that?
The only evidence I have for the new phase is the open circuit voltage, which shows that there is a region on the surface having a higher chemical activity of the material that is present in the beta phase, which this phase decomposes into. Simple logic says that palladium deuteride has got to convert to something else. I mean, everybody, every theoretician says, look, that phase doesn't have the characteristics to make it work. I mean, that's what everybody concludes, and I think is absolutely right. But also, simple logic says that you've got to have something different because we have all kinds of samples of that stuff, and you see nothing until something special happens. Well, the specialness is the formation of that phase on the surface I'm proposing. Now, what the nature of that phase is still up for grabs. I have my own ideas, other people have their ideas, but we'll see.
Okay, thank you.
Thank you very much. Last speaker of this session is Dr. Loncha. Title is Reproduction of Fleischmann and Pons Experiments. Bivrian. No, speaker is Dr. Bivrian.
Okay, thank you very much. This is a very challenging talk, not because of the subject, because of the time. I have to fight with about 200 stomachs, so it's a bit hard. I want to say first that I feel like almost in paradise here. In Japan, I feel taller. Here, I feel younger. And I almost speak fluent English. The only objection we have to paradise is the sexual discrimination we have here. But that can be solved maybe in the future. Before starting, let me just play as a mailman and passing a standpoint correction of the weight of these samples. So for those who want to make right numbers, like Professor Lee, to give you time to write down the weights and volume of the electrons. Okay, this talk, actually I'm not Dr. Georges Longchamp. I'm Jean-Paul Biverian, and I'm talking in his name because he thinks his English is not good enough, so I think he didn't want to have a hot seat either. So anyway, this program has been started by the French Atomic Energy Commission under the direction of Georges Longchamp in collaboration with the School of Electrochemistry in Grenoble. The idea of the program is to check the validity of the cold fusion results obtained by Fleischmann and Pons in 1989. I have always a lot of talks with Georges Longchamp about that. He's very surprised that nobody is trying to duplicate exactly the original experiment. He doesn't know that this audience is very special. Scientists don't like to duplicate other experiments, and especially those here don't like that. They want to go on their own and make new discoveries. This is the nature of science, which is, especially of scientists, discover new things and go new fields. So these are extremely creative people. I think we are at the edge of the edge here. So the objective of this project is to check the validity of the claims and by reproducing the exact one without any modification, because that's the key to resolving some of the contradictions that people have. Everybody is doing his own experiment and nobody can check the validity of the other one because nobody is doing the same one. So this cell, you already know that cell because that's the exact cell that has been used before by Fleischmann and Pons. I just want to, where's the laser? I just have this stick. That's okay. Anyway, so this is a D-warp tube, glass tube, glass dewar, about 20 centimeter high, 25 millimeter in diameter. It's evacuated with a good vacuum. We have a cathode at the bottom of the cell, surrounded by a platinum anode. We have a thermistor in the middle to measure temperatures, a resistance heater for calibration purposes, and the top of the cell is covered with a silver coating in order to to control exactly the heat loss by radiation. So the heat loss is happening only in the bottom part, not in the upper part, which is silver coated. The electrolyte is lithium hydroxide. And what else did they say? The whole system here is computer controlled so that as electrolysis goes on, some of the water is dissociated and lost and replaced automatically by clean water automatically. Here is a complete design of the system. It's not very complicated. We just have a PC that controls the power supplies, and we measure constantly the temperature of the bath and the temperature of the cell. The temperature of the bath is accurate within 1/100th of a degree, and we measure the temperature of the cell in the middle here. Because of the unique position of the anode, the anode and cathode being at the bottom of the cell, you have constant mixing of the water, and the water is uniform all the way through the top. Now, okay, again, this is not new at all. This is very well known. This, for those who have looked at the details, the energy balance proposed by Fleischmann and Pons. The excess heat measured is the difference between the radiative heat transfer to the water bath. This is the traditional radiation coefficient, K, which is which depends on the geometry and the dimensions and the surface, the nature of the surface of the material, and the temperature of the cell and temperature of the bath at the force power. The enthalpy of the content of the gas stream, this is a bit more complicated to understand, but this is the water. This is carried away by the hydrogen, deuterium gas, and oxygen gas that is released. The pressure here is the pressure of the water at the temperature of the cell. P star is the pressure of the water at the actual atmospheric pressure in the room. So as you raise your temperature, the denominator becomes closer and closer to zero, and you're carrying away a lot of water. So this term is very, very important at higher temperature. At low temperature, this term is very negligible. If the temperature of the cell is changing, you have to take into account the change in the enthalpy of the content of the calorimeter. If the temperature is almost constant, this term is also negligible. But if you are in a position where the temperature is changing fast, then you have to take that term into account. And finally, you have to reduce the heat you are putting in the system due to the electrolysis, which is the voltage across the cell between the anode and cathode, minus 1.54 volts in the case of heavy water multiplied by current. So this gives you the excess heat. So in that equation, we suppose that all losses are due to these numbers here. We don't assume there's anything else. There's no conductive losses. If there is any conductive losses, this should be seen in the calibration with platinum cathodes. Typical run is as follows. We work for some time at low current, like 0.2 amps. The temperature in that case is low, below 40 C. And then after 1 or 2 weeks, to raise the current to 0.5 amps, and the temperature goes up. Now, we have to understand that cell, the mechanism that's happening. It's not obvious that it's happening in the other cells, but because the walls of the cell are made of Pyrex, the lithium hydroxide react with Pyrex and make lithium silicates, and they deposit on the cathode and the anode. That produce an overvoltage. The overvoltage, because we're working with constant current, forces the voltage to go up, and the input power goes up. The input power increase makes the temperature rise. So rise up to boiling. So we can get boiling with platinum, but it doesn't prove that there is excess heat with that. You can get boiling just like any heater. So if there is an excess heat, it is something that's due to something else to this effect. This is true for platinum and for palladium. Let me show you a typical experiment here. This is in days. You have 3 axes. This experiment lasted 33 days. This is a high-purity palladium cathode from Johnson Matthey. You can see in the blue line is the current, the 0.2 amps, then 0.5 amps, going up stepwise here. You can measure in the blue and in red the set temperature. You can see the cycles due to the pulses in the resistor heating we have in the cell. Temperature going up. And this is the enthalpy input, the number of watts we are putting in the cell. It's going up, as you can see. Now, the first part of the experiment is at low current. It's just for loading. So this is not the part we're using in our analysis. Nothing is happening there. Now we have, however, 2 regimes. The low temperature regime at below 70 degrees C, the temperature is low, so the enthalpy in the gas stream is low, it's negligible. And because the temperature is almost constant, we don't see there is no effect due to the enthalpy of the calorimeter. So the only terms we have are these 2. When you go to intermediate regime between 70 and 99 degrees C, you have to add all the numbers here. Now, at boiling, and when you get very close to boiling temperature, first of all, you have to realize that in that case, you never reach boiling. And the reason why we never reach boiling is that the gas stream contains both water and hydrogen or oxygen. So the bubbles are not pure water bubbles. So you never really reach the boiling temperature. So it's an asymptotic behavior. So, and what's happening, this term here, at high temperatures, because the denominator is so small, you get a huge number, and the error bars are so huge, you can't use this equation anymore at high temperatures. So instead of that, we use another procedure which was used. I mean, this is exactly the same, the replication of Fleischmann and Bond's experiment. We measure the amount of water lost during boiling. What's interesting here, you're working at constant temperature, almost constant temperature. And the excess heat now is the enthalpy used for vaporization of the whole content of the water. We stop putting water at one point, and then we measure the amount of heat we have put to vaporize all the water. And so there's a difference between the enthalpy used for vaporization minus the available enthalpy, because we realize if there was no excess heat, this should be 0. I mean, we put number of watts and you evaporate the number of cc's of water. And this available enthalpy is the input enthalpy minus the losses to the bath water, the radiation losses. So here is a calibration experiment with platinum. So this helps us believe in the numbers I mentioned before. In this curve, you can see in black the enthalpy input, the watts we are putting in. This is the second part of the experiment when we jump the power to 0.5 milliamp. This is the set temperature going up, and this is the excess heat. So it's not exactly 0 because, as I'm telling you, there's some errors. The model is not perfect. It's fine, it's okay. So you see that we can go up to about 0.5 watt of resolution at high current. This is the same curve, but the blue is in percent, so it's about 0.5% resolution, sensitivity. Now, if you go to palladium cathodes, you can see that there is excess heat coming up here. Now, in that experiment, if you see a drop in temperature, this is a problem that Mr. Longchamp has. And we used to have babies on Sundays, now they have ways to have babies only on Mondays. So here, in that case, when you start the experiment, there's no control. Now, for babies, they have controls. We don't have control, so we don't know when the experiment will just start boiling up. So it happens most of the time like at night. This is another problem. This is due to the... So yeah, in this one case, he stopped, he slowed down the experiment, so that's what happened here. This one has been cleaned up in aquaregia, palladium cathode. Again, excess heat showing up here, all the way. This one is interesting because we have a hard time finding the plus from the minus in the power supplies. And initially we made a mistake and we used the palladium as an anode. It took us 3 days to realize there was something wrong there. And that helped a lot, actually. So most of the big discoveries that we made by accident, we are trying to make as many as we can. There's no problem with that. Some are not that good at all. Anyway, this one seems to work very well now with these 3 days inverse polarities. That's the same one in percent instead of being in so you see the percent is 2.53% excess heat in this low regime. So the number at high temperature, hard to determine accurately, so I won't talk about it. Another one, I will go quickly, because time is short, and your stomachs are fighting again, you can feel it. Another one here, again a few percent excess heat at low temperature. And now, let me show you a typical boiling regime, which is the interesting part of the experiment here. This is the last part, the boiling regime. At about when the temperature reaches about 99 to 100 degrees C, we stop putting water in it, and we measure the total amount of energy we have put in the system and the cell temperature. You see the cell temperature very slightly. And let me show you the same thing with the calibration. Let me show you these two graphs, maybe almost to get the same position. If you look at this platinum one, the enthalpy input, because you're working with constant currents, you can see this corresponds to voltage. So the voltage goes up, and slowly is going up here. Now, in this one, this is palladium. You see a big jump in voltages here. So something is happening at the end of the experiment. So out of the 1 hour time experiment, at the end, something is happening here. And if we follow the loss of water continuously, we realize that in the first part of the experiment, there is no apparent excess heat. I mean, as accurate, as precisely as we can measure it by measuring the level of water. But at the end, there's a lot of losses. And this corresponds to this big jump in overvoltage. As I was telling you, the overvoltage is due to the deposit of silica or silicon on the anode and cathode. But something else is happening at the end of this experiment. So to terminate this thing, just to give you this big table. Everybody has tables, so I have one, and nobody can read it. So I have to read the thing, but I need it to have it, so that nobody knows you shouldn't have it. So we can go up to, we have 16%, 0%, this is platinum, and the other ones are 18%, 3%, 7%, 20%. This is total excess heat during boiling. But if you look at the end of the experiment, just the final thing, we call it the grand finale, you know, when the, well, if you're a woman. This is, you can go up to 150% at the end of the experiment.
There is one.
There's one. I know there are few names. I don't want to offend them, that's why I say it. So let me conclude because they're jumping around. Let me just end up by my conclusion. So first of all, placement and pond calorimetry is very accurate. Within 0.5% we can give data, numbers. And we're adapting to this work. But you have taken a lot of precaution because it took 3 years to launch and to learn how to operate this cell. So you have to be very clever, very smart, and very careful during the experiment. The deworm must be excellent quality to have only radiation losses, no conduction losses, otherwise it will not work. Calibration of thermistor may be very accurate because you are measuring different steam temperature and force power. Current care is taken to minimize the thermal losses by heat conduction, that will also destroy your calibration. And very well sealed off electrical feed-throughs, otherwise you will lose water through the feed-through. So our final conclusion is that below 70, for the platinum, below 70 degrees C, there is a very small apparent excess heat, which is due to the heat conduction, we believe, which is not included in our equations. And between 70 degrees and boiling, the factor due to the gases carried by the gases, the water carried by gases can be used accurately in this area. But at boiling, we detect no excess heat. With palladium, we get between 0 and 5% excess heat below 70 degrees C. Same problem at around 70 degrees C, and at boiling, large excess heat, up to 150% is generated. So I wanted to say something about future, but for the first time in my life, my wish had been accomplished before, because we need to have permanently operating cells at boiling so that they work. And Stanford just did it before I even talked about it, so that's the first time in my life it happens. I have to say that to my wife, she might be happy. It happens sometimes. Thank you very much.
So, paper open the discussion. What is it?
One of the most interesting points about the placement ponds experiment was observing life after death. Did you observe life after death?
No, we didn't observe life after death.
Ikegama.
How could you estimate the large excess heat, like 150% at the end of the boil?
That's just by evaluation of the level of the water at the end and measuring it. I mean, we knew how much we had lost roughly. I mean, this is not very accurate. The last part is not accurate in the percent. I mean, the number 53, I mean, you can forget about the 3. Even the 5, maybe. It's not very accurate. This part is not accurate.
No. How could you define the level of,
we can see the level of the water.
Yes, but that's boiling.
I know, but you can estimate. It's not very precise. I agree. It's very precise for the total. It's not very precise for the
When it is not precise, how could you say 150%?
Well, plus or minus, I tell you, it's, should I put 100 plus or minus 50%?
Plus minus 50?
Yeah, it could be that.
Could it be 200 then?
No, it can be 300. It could be,
Okay.
no, it could be 200, it could be 100. Yes, that's true.
Sanchez.
In reality, that speak about estimate 2% is really meaningful. Do you really feel it?
Oh yes, it is meaningful. The 3% are meaningful. Yes, they are meaningful. We have a lot of cases. I mean, I didn't show you the samples that don't work. We have the 0%. We know we have 0% also. Some palladium, a lot of palladiums actually, we have 0%. I show you the calibration curve. You have to be extremely, extremely careful with the cell and with preparation of the cell. I agree.
Okay, sorry, but I have to stop the session because you time.
Thank you very much. We will now end the morning session. Dr. Kasagi, please.
Ladies and gentlemen, we'll start this session. I'm Joe Kasagi from Tokyo University.
Elegant Count from NAG Lab.
As you look at the program, so many speakers in this session. So we have to follow the rule that yesterday Mr. Matsui told, so that each person has only 2 minutes. It's a reverse rule. So we have a chairman has we have right and power to stop the speak, okay? So I'll call the first speaker of the session, Dr. Aoki. He will talk about search for neutron emitted from sodium tungsten bronze.
Thank you, Chairman, for your comments. Good introduction. The title was Search for Neutrons Emitted from Sodium Tungsten Bronze. The purpose of this experiment is to determine the experimental conditions for good reproducibility of neutron emission from sodium tungsten bronze. 3 years ago, Rushden Group firstly succeeded in obtaining a good reproducibility. We followed their experiment, and we can show here our preliminary results. After applying a cathodic treatment to the crystals in a heating chamber, a neutron emission had been expected in the instance of pressurizing and depressurizing deuterium gas. However, the weighted mean values of measured neutron counting rates at these moments were in agreement with those of the background rates. Therefore, a clear evidence of the neutron generation was not obtained yet. This shows the neutron counting rate and the deuterium pressure as a function of the time. Red line shows the pressure of the deuterium gas. Above shows the neutron scalar D, and the middle is the neutron scalar A. They are operated independently. So, the expected counting rate this time the pressure is increased up to 100 torrs. This time the pressure is evacuated to 0 torr. Therefore, green circle is the expected counting rate at this instance. However, we cannot observe any increase of counting rate.
So time is running out.
Oh, okay.
You should go say something.
Okay, all right. Thank you very much.
Okay, the next poster is P34. It will be presented by Dr. Okamoto.
We have measured neutron energy spectra in an electrolysis experiment over a long time using a liquid scintillator LE213 with a neutron gamma pulse shape discrimination. We found the counting rate of the detector changes with detector temperature. During electrolysis, the cell gets hot, and it heats up the face of the detector, and the counting rate changes. In conventional nuclear experiments, this problem does not occur. We report the effect of temperature on counting efficiency of LE-213 for low-level neutron measurements. The counting efficiency decreases when the detector temperature rises. We think this is caused by a decrease in fluorescence emission. We conclude that in neutron spectral measurement by the LE-213, where the temperature of foreground is different from background, a correction is needed for background data. Thank you.
Okay, thank you very much. And next poster is P35. I'm asking Dr. Chan or Liu. Is there? No? Okay.
I understand also that the number 36 will also not be presented. That leads us to P37 on the cold fusion miracles, Dr. Chen from National Tsinghua University in Taiwan.
Good afternoon, ladies and gentlemen. I'd like to just mention two things in my experiment. The first one is the excess heat for both palladium heavy water system and nickel light water system. We've got several heat bursts during the electrolysis, and the result are shown on my poster. And the other thing is for nickel light water system, we've got the nuclear ash for example, calcium to from the preliminary result to 1 to 2 orders of higher in calcium. That's all I want to report here. Thank you.
I also believe that P38 hidden results of ion band state theory is not presented unless is Dr. Chubb here. If not, we'll move to P39.
P39 title is model for neutron emission from condensed matter. It will be presented by Dr. Kobayashi.
We try to propose a quantum mechanical model for the neutron emission from condensed matter. This model is based on the two new phenomena. One is the total disintegration of a deuterium molecule, and the other is the subsequent dipole disintegration of a neutron. We calculate the probabilities of the neutron emission from condensed matter. We consider the mechanism of the dipole disintegration, especially the transition from the ground state to the jetting state. Please look at this figure. This figure shows our results. Our result of the numerical calculation shows that the important features of the neutron energy spectrum can be successfully explained by the dipole disintegration, especially the main peaks of the neutron energy spectrum and the large filling ratio. This implies that the this implies that 2.45 neutrons can be predicted by the dipole disintegration instead of the DC nuclear fusion. Thank you.
Okay, thank you very much.
The next papers will be numbers 40 and 41 by Dr. Young Kim from the Department of Physics in the Purdue University in Indiana, and his co-author is Alexander Zuberev.
Do I get the 4 minutes?
Yes.
Oh,
That's how you get around the time limit.
so what about
You've got 3 minutes and
later
45 seconds.
presentation?
2 minutes for each paper.
Oh, 4 minutes, okay. Very good, because I want to omit one paper. Explain the 4 minutes. This paper, physical review letter paper by Leonard Bain, had devastating effect for cold fusion because this is about time EOA is making up their mind. And I'm going to talk about this exact upper bound cannot be established. What it is this is a Schrödinger equation with Born-Oppenheimer potential, and based upon the got exact upper bound, and that upper bound is given here in this form. This laser in this form. This is famous gamma factor, and this is not too large, like a 60 or so. So essentially it's saying that you can overcome the gamma. There are 2 problems with that approach. If, even though it's equilibrium, if deuterium is moving, yet equilibrium, there is no bound for this integral, which means the formulation they come up with only applies to real bound state. But in the electrolysis, that is not satisfied. That's one problem. Second one is the conventional formula everyone uses. That the reaction rate is related to probability of finding particle at the 2 particles at 0 distance times some S factor. But this is semi-classical expression, and you don't know whether that's good or not. You have to do quantum mechanical calculation. And quantum mechanical calculation we derive is different. So there are 2 problems with this approach. So we, to convince ourselves, we did some calculation with non-local potential. We introduced, in addition to Coulomb interaction, introduced positive separable potential. So this will be worst scenario. In addition to Coulomb repulsion, you have an additional repulsion. And you can solve the Schrödinger equation, and the solution look like this, and this is ordinary Coulomb wave function, and this is additional effect due to this additional potential. This can be done analytically, no numerical budget. And what we come up with this statement that instead of conventional estimate based upon this term alone, first term alone, that corresponds to essentially Leonard Bain's upper bound. Actually, that this term, this is that one. But this additional term can add this contribution. Of course, you have to square it. Just pull out the square of each term, the additional term. But that can diminish gamma factor if beta happens to be large. What this means is that if effective interaction between deuterium and deuterium in the media has an effective potential which has a long range. You can overcome this first term. So that this is a comparison of formula. This is an example showing that this is not very exact statement.
Professor, can we conclude?
Yes,
We're out of time.
I just concluded.
Okay.
Any last?
Okay. We'll go on next. Poster. The 42 analysis of the electrolytic cold fusion experiment on TNCF. Kojima, Horie, Nomura, Okita.
Hello, I prepared a presentation of the analysis of electrolytic experiments on TNCF model. This TNCF model means trapped neutron catalytic fusion. A TNCF model was proposed by our teacher, Dr. Kojima. It assumes the existence of thermal neutron trapped in cold fusion materials. There is a strong possibility that the thermal neutron is the origin of the cold fusion phenomenon. We calculated typical experimental data of electrolysis and obtained consistent results, which explains the tritium anomaly. That is, large ratio of P by N. And we evaluate the neutron density in the materials. And I'll explain the method of this calculation. It's very easy for you to understand. I'll introduce this model to you, and I'll explain about the following questions. Why can neutrons be trapped in the cold fusion materials? Why can they have so long lifetime that it can fuse with other particles? But I'll explain just simply, because we don't know that well yet. Please come and ask me later. Thank you.
Thank you very much. Next poster is P43 on the existence of trapped thermal neutron in cold fusion materials, presented by Professor Kojima.
I want to show you the existence of the trapped thermal neutron in cold fusion materials. By the analysis of experimental results and also by some physical basis. This model is phenomenological and assumes the trapping of thermal neutrons in specific region of the crystal and the stabilization of the trapped neutron and the destabilization of the trapped neutron by a perturbation. And the destabilized neutron induces trigger reactions. The generated energy particles induce bleeding reactions. We analyzed more than 15 experimental data obtained at Hideo and obtained a number of neutrons trapped in trapped in the crystal as a parameter and compare experimental result with theoretical one and agrees in one order of magnitude This is the experimental basis for the existence of cold fusion. And we will explain the theoretical basis for the existence of stable neutrons. Please come to our bars and discuss together to proceed the cold fusion physics. Thank you.
The next paper, P44, actually will not be presented. That brings us to P45, nuclear reactions in condensed media for interaction of charged particles in energy region is forming by maximum elastic losses, and that will be presented by Professor V.A. Romadana from the Luce Institute and co-authors. Dr. Romadana. Well, if Dr. Romadana returns, we'll present out of order. And that brings us then to P46, investigation of nuclear emissions in the process of deuterium escape from deuterized plate foils by Dr. Lusetzi.
Hello, ladies and gentlemen. I would like to present the results of investigation of nuclear emissions in the process of deuterium and hydrogen escaping from vaporized and hydrogenized palladium or palladium samples and palladium or palladium samples. As was shown in this reference, the palladium samples demonstrate the anomalous thermal effect and neutron emission in the process of deuterium escaping from these samples. This effect was reproduced in many series of experiments performed by Dr. Lipson's group from the Institute of Physical Chemistry, Russian Academy of Sciences. Such samples demonstrate the same properties. We used the following detection methods to observe the neutron emissions. The neutron detector, the plastic scintillation detector, silicon semiconductor detector, and plastic jack detector CR79. The results obtained by independent detection methods are in good agreement with each other. It was observed the emission of protons and neutrons in the process of escaping material or vaporized and vaporized samples. The ratio of proton and neutron fluxes was estimated as approximately 1. The charged particle emissions was also observed in the process of escaping hydrogen from hydrogenized samples. The emitted charged particles may be identified as protons and alpha particles.
Professor? See, we're out of time, so we'll, I hope that we'll follow up.
The next poster, P457, will not be presented. So we go on to the next one, P48, detections for nuclear product in transport experiment on deuterium through palladium metals. Dr. Shimajima, Nishioka, Shikamo, and Kanpei. Shimajima will present.
Since Yamaguchi and Nishioka have reported that they detected helium-4, which is direct evidence of nuclear fusion, we have studied deuterium dynamics and nuclear fusion in perihelium to reproduce and investigate the anomalous phenomena. The deuterium transport through perihelium, which we report in the present work, is a good process to study and understand deuterium dynamics and nuclear fusion in perihelium. In the transport experiment, we try to detect the nuclear product, such as proton, triton, 3 helium, neutrons, and helium-4, in order to confirm the occurrence of nuclear fusion in perihelium in this time. However, we could not detect any nuclear product in the transport experiment. In addition to discuss about the transport experiment, we will also talk about the experimental result of low-energy deuterium ion bombardment, in which we used ECR ion sputtering system as an ion source at the deuterium ion energy of 2 keV. Thank you.
Okay, next poster is P49, search for anomalous nuclear reactions in PDDX by detection of nuclear product in vacuum gas system. Will be presented by Dr. Taniguchi, Dr. Kaji, and Dr. Takahashi.
We perform nuclear recording without heating experiment to detect nuclear products. The aim is to detect charged particles, neutron, and helium from samples heated in vacuum. This figure shows the experimental system. Sequence of this barrier detector was set for charged particles spectroscopy. ME213 scintillaton counter for fast neutron spectroscopy. And quadruple mass spectrometer was connected with the chamber for gas analysis. This figure shows an example of experimental results on neutron measurement for the gas loading experiments. Some data points exceed 3 sigma level. However, background neutron level was comparatively high throughout the experiments, and fluctuations were so big that the increase of neutron events might be attributed to the change of background level. I will explain the results of these experiments in detail in the post session for charged particles and mass vibrating and so on. Thank you.
Next poster, P50, diagnosis of neutrons from gas research facility. Dr. Wang, Chen, D, Yu. Not here, sorry. So we'll go on P51. Search for tritium in palladium plus D system by a gas proportional chamber. Dr. Yoshikawa, Aoki, Kurata, Ehihara, Mori. Dr. Yoshikawa.
Our title is Search for gas proportional chamber. We made gas proportional chamber and measure some sample properties. So we are presenting the result of this chamber. This is X-ray spectrum and the tritium spectrum, and this is the calculation curve. This spectrum corresponds to tritium as several vectors. So we put the chamber 1 vector to 7 vectors tritium. And this is a count of chamber, linearity vector. And also we presenting there are some results, spectrum of background and the sampled gas spectrum, or integrated result of the integrated spectrum. Until now, we chamber only response to here include the tritium gas. This is 1 vector tritium to 7 vector tritium outside vector. So this chamber is now working, and this chamber is always available. So if you want to use or if you want to measure by this chamber some gas, we will be happy. So please come and discuss with the center.
Next poster P52 will not be presented. So we'll go P53. Hydrogen isotope effect induced by neutron irradiation in PD LIOD electrolysis. Dr. Oya, Ogawa, Ono, Aiwa, Okamoto.
The title of our study is Hydrogen isotope effect induced by neutron irradiation in PDLIOD electrolysis. We examined to find the thermal and external neutron irradiation effects from PDLIOD and LIOH electrolysis. The experimental system, including the electrolysis cell, has been modified to perform the neutron irradiation experiment. The neutron irradiation was repeated in every other day into the electrodes through a collimator for 26 to 30 days. The neutron energy spectrum was obtained by the same method reported previously by our group. Excited up to 2.5 watt, that means 10% of input power, and anomalous neutron energy spectrum were observed in the thermal neutron irradiation experiments. But we cannot find any anomalous result about gamma ray measurements. In the external neutron irradiation experiment, we found anomalous neutron counts. In this study, in this session, we discussed these anomalous results. And we always welcome to your comment, suggestion, and question. Thank you.
Next poster, P54. Deuterium fusion experiments on metal foils implanted with deuterium beams. Presented by Dr. Uchiai, Ida, Beppu, Maruta, Miyamaru, Takahashi.
The nucleus of fusion reaction in solid may explain the fractional constant effect. So we have performed the beam implantation experiment to measure the high energy charged particles, which are supposed to be produced by the nucleus of fusion reactions. We also introduced some additional techniques in the experiment, namely molecular beam implantation, temperature control, and pulse standard stimulation. Moreover, we have tried to measure the high energy particles reported by Kasami et al. This showed the apparatus of the experiment, and various kinds of sample foils were implanted with deuterium beam of 150 to 250 keV energy. A pair of silicon semiconductors were used as the detectors for high energy charged particles. Also, a ceramic device with coolant water loop was used for the temperature control of the samples. And this shows the example of the result of the experiment. As you see, here is DD proton, and power edge, and some counts in high energy region over 6 MeV. These are unidentified signals. I will explain the detail at the poster. Thank you.
The next poster will be P056, lattice-induced reactions from Dr. Peter Hagelstein of Massachusetts Institute of Technology in America.
Most people in the field assume that fusion reactions are at the heart of what's going on. My conjecture is that if there's anything nuclear going on, it's likely not to be fusion, and that there's energy transfer between the lattice involved. My conjecture as to how that works, one way it might work is if you have a large number of phonons in the lattice before a reaction, if the reaction occurred, then the phonons in the mode would have to project into final state modes, which would give a distribution of energy for the final state lattice. This distribution translates into the probability of energy transfer. The resulting model is just an integral of the probability of energy transfer with the reaction rate. To get a large number of phonons, the proposal is that we exothermically desorb and drive a phonon laser. I've applied this model to a variety of possible reactions. In the case that we have alpha decay, we can get some very large alpha decay rates. Palladium and nickel are stable against these things, but samarium, cerium, and platinum have finite reaction rates. And this is interesting because heavy materials would be exothermic under lattice-induced alpha decay. Light ones would be endothermic. The best fuels, if this is the heat mechanism, can be identified. Samarium is about the best stuff. In the analysis of Fleischmann's cathode that has cerium and has some samarium in it, I've applied the model to the activation described by Pascal at the last ICCF, and the model seems perhaps to be consistent with a lattice energy transfer of 350 kilovolts that can happen essentially CW over the time of the results.
We're out of time.
Thank you.
The next paper will be P60, I believe. Numbers 57 and 58 and 59 will not be presented. That's anomalous phenomena in E less than 18 keV hydrogen ion beam implantation experiments on palladium and titanium. That will be presented by Dr. Wang from Institute of Modern Physics at the Chinese Academy of Sciences in China.
Excuse me, I have 2 posters, so I need 4 minutes. Okay.
Don't trick me like that.
The title of my paper is about low energy implantation experiment. And this is abstract. In our experiment, proton and neutron beams with energy from 1 keV to 18 keV have been used. The intensity of the beam is about 1 milliamperes per square centimeter. And X-rays, gamma rays, and neutron charged particles have been measured. Some anomalous X-rays have been measured. This is an anomalous peak in the X-ray spectrum. This is normal area. Generally, this is low energy soft X-rays, and here is energy about 10 keV. We used only 18 keV beam, but we got such a peak, such a 60 keV. And this peak is moved with the increase of beam energy. This answer is beam energy, and this is peak position. Both of this with energy in keV. And this peak, half-width of the peak is reduced with the increasement of beam energy. You can see this is some X-ray spectrum. This anomalous peak, this width of the peak reduced rapidly with the increasement of beam energy. This is some spectrum from neutron-close palladium experiment. And this is some anomalous spectrum from proton-close palladium experiment. And we have used the titanium instead of palladium. Similar experiment phenomena have been observed. And this X-ray spectrum is with very low intensity of the beam. The beam intensity is about 7 microamperes per centimeter. So the first spectrum is about 30 minutes, and this anomalous peak changed and moved. This is after implantation about 270 minutes. That means the anomalous phenomenon depends on the implantation dosage. And some neutrons and charged particles have been also observed. This is a charged particle spectrum. And this answer is neutron intensity. This answer is charged particle intensity. We can say this curve is a linear curve. So I think the neutron intensity and the charged particle have some corresponding relation. So we think neutron is DD neutron and charged particle is proton. But from this spectrum,
Dr. Wang, we're out of time, I'm sorry.
okay.
I understand that P62 will also not be presented, bringing us to P63, cold fusion in metal deuterides and manifestation of the dark matter of the universe. Pardon? Is Dr. Drobiszewski here? Okay, that brings us to P64.
P64, observation of nuclear product in gas release experiment with electrochemical deuterium palladium, presented by Makoeto, Yamura, Koto, Toyoda.
We previously reported on mass number 5 gas increase in gas release experiment with electrochemically deuterated palladium. Gas release experiment is as follows. A palladium is electrochemically loaded like this, and after that, we heated deuterated palladium up to 180 degrees to release the absorbed gas under vacuum condition. We detected mass number 5 gas using mass spectrometer. Mass number 5 gas is composed of DD and DDH. We monitored mass number 5 gas and mass number 1 gas hydrogen and investigate the effect of hydrogen concentration. We developed gas sampling system to store release gas and analyze hydrogen concentration of the stored gas using mass spectrometer. After that, we introduced background DDH intensity taking account of DDH formation depending on hydrogen concentration. As a result, mass number fire gas intensity cannot explain by the existence of hydrogen, and the mass number fire gas time evolution does not correspond with hydrogen. Therefore, we conclude mass number fire gas is composed of DT gas spectrum.
Next, P65 is not presented by preview, but the poster is over there. Oh, yes. I don't think P66, author of the P66 is not here, so we pass it.
The next poster will be P67, transmutation phenomena in the palladium cathode after ions irradiation at low discharge, by Dr. Sanatimova and co-authors from the Institute of Luch in adults.
It was shown that the change of the separate impurity elements, composition and isotope after radiation palladium cathode by ions at the low discharge plasma depends on the structure of the cathode material, content of the working environment, ions flow density, and the location of the analyzed layer concerning the surface. Then, the greatest changes of isotope ratio on the palladium cathode in comparison with natural abundance appeared after radiation by argon and xenon ions. For example, palladium 104 increased by 2 times in comparison with the protium irradiation. The group of certain impurity elements repeated after radiation under similar condition by ions hydrogen, deuterium, argon, and xenon. Such elements as chlorium, phosphorus, scandium, titanium, vanadium, bromium, germanium, arsenicum, krypton, strontium, and other was we can see, we observed. The quality of adding impurity elements after ion radiation decreased in the next in the follower order. Deuterium, hydrogen, and argon and xenon. Maximum increase of impurity qualitatively related with maximum of the excess heat in process of ions radiation of palladium cathode at low discharge. Oh, excuse me.
Professor Sabatino, we're out of time, I'm sorry.
Oh.
Dr. Jang, number 68, concentrated energy and micronuclear fusion. I believe that's being presented at spot number 66, but I think he has come. No, okay, I know. Okay, please, 70. Is Dr. Romadano here? Okay, Professor. The tritium generation and transfusion of hydrogen isotopes to the target in plasma or discharge. And Professor Romadano, if you'd also like to present P45 at this time, you're welcome to do so.
tritium generation and transfusion of hydrogen isotopes through target in plasma of powerful low discharge. Experiment was carried on was installation with hermetic sample of molybdenum, tantalum, niobium, vanadium. For use hermetic sample, we use diffusion hydrogen out inside the volume sample to inside sample. For this condition, rate tritium generation in long time have very big range on 3 order, but minimum tritium generation rate higher than background on order. For vanadium, niobium, and tantalum, it is not recorded influence transfusion hydrogen through material sample. For molybdenum, tritium generation rate increasing in 2 times with transfusion hydrogen out inside to inside the sample. Experiment with protium in this installation showed in beginning experiment tritium generation rate was equal for deuterium, and with time decreasing for very long time, about 200-300 hours. The rate of transfusion on the deuterium flow is directed in opposite side to direction of flow for bombardment ions has not rendered the significant influence on tritium generation rate for sample of vanadium, niobium, and tantalum, for sample of polycrystal and semi-crystal molybdenum. The efficiency of tritium generation was increased at transfusion approximately on 2 sides. The tritium generation rate for sample from polycrystalline molybdenum at use of discharge of protium with major concentration of deuterium by decrease from maximum significance for the deuterium and was established on level of significances on order exceeding background ones. The time of achievement of satisfactory significance of tritium generation rate exceeded 200 hours.
I'm sorry, Dr. Romanov, we're out of time.
Next, maybe.
In the poster session, of course, we'll discuss it in much greater detail. This is only one introduction. So the next paper will be P72, Energy Generation Processes and Cold Nuclear Fusion in Terms of Schrödinger Equation by Dr. Sapogin from Department of Physics at Technical University Mallove in Moscow.
I am Russia. My name is Sapogin, Technical University Physics Department. Name my report you see. You see, that's the Schrödinger equation. I use very complex substitution. This substitution appears in a ring. After use, you see that first member for small energy neglected. After it and differentiation, you see that for very short distance time, member 2 and member 4 equal. You see, you obtain this equation from which I have possibility obtain moving equation. I solve this moving equation for interaction from nuclear for Coulomb potential. After solution, you see that minimum distance between nuclear may be very small for very small energy. Thank you.
The next poster will be T74, structural changes of single crystals in neutron generation experiments. The authors are Vakarin, Samgin, and Andreev from the Institute of High Temperature Electrochemistry in Ekaterinburg, Russia. And the presenter is Dr. Samgin.
It will be me. I'm sorry.
Oh, excuse me.
We too don't represent you. Single crystal samples of oxide bronzes are capable to become prospective materials for cold fusion. Different experiments on reproducibility and search for neutral generation using crystal of oxide tungsten bronze were carried out in recent years by some research groups. However, positive results were obtained only for a number of experiments. We have shown that neutron generation is observed in crystals which have sufficient perfection of the crystal working plane at the beginning of the experiment. The direct influence of test conditions on reproducibility of results has been demonstrated. It was assumed that the neutron's generation occurs at the moment of distortion of the lattice channel structure. Having used the X-ray method, we have observed the lattice structural changes in samples with positive results. This phenomenon testifies to the fact that some explosive process may take place inside the crystal lattice. Thank you.
I'm sorry, I inadvertently skipped P73. New experimental results and analysis of anomalous phenomenon in gas glow discharge, and the presenter will be Dr. Zhang from China.
Your experimental results and analysis of anomalous phenomena in gas discharge counts and energy spectrum of X-ray have been registered in gas discharge. There were some anomalies in about 100 energy spectrum. When discharge water rate was 4 to 14 kilowatts, there were 30 to 300 kilowatts continuous X-ray. Their intensity were 10% to 1,000% of background. It is energy, it is counts, it is background. You see the high energy there is. in numerous cases, the maximum energy of X-ray was like this, but the measuring energy was as high as 10 to 20 times of this maximum energy. So we use the different thickness metal attenuation for in front of the detector, the mass attenuation cross-section mu overload might be obtained in comparison with the standard value mu overload star of handbook mu over mu star equal to this. It is very different than 1, and the mu overload dependent not only EX and the atomic number Z, but also VL3 negative absorption. For check and comparison, we also applied DLD for measurement of X-ray dose. We obtained mu overload equal like this. The corresponding X-ray energy was 214 and 277 kilowatts. This strongly supported there were 100 to 300 kilowatts high energy X-ray in lower voltage discharge. We suggested some explanation about anomalies.
Professor, I'm very sorry we're out of time.
The next poster is P75. Carbon production on palladium point electrode with neutron burst and the DC glow discharge in pressurized deuterium gas, presented by Dr. Yamada.
In this current investigation, a very simple electrode system of point plane gap configuration in 2 atmosphere deuterium gas is used to confirm the so-called cold fusion. DC voltage of positive quark or 8 kV is applied to the palladium point electrode during the excess neutron counting time of 24 or 25 up to 65 hours. And neutron burst occurred in 2 out of 37 rounds. Using an optical microscope, a drug deposit is observed on the surface of the positive palladium point electrode after the neutron burst. To the contrary, we have the surface of other 35 palladium point electrode has kept its beginning appearance of silver color. X-ray photoelectron spectroscopy shows the drug deposit to recover the total amount of carbon impurity in the palladium point electrode and in the environmental deuterium gas doesn't account for the large amount of carbon on the surface of the palladium point electrode. I'd like to exchange information on this phenomenon. Thank you.
Okay, the next poster. Piece 76. A study of the mechanonuclear interaction using the piezoelectric material LiMeO3 in D2 atmosphere. Dr. Utsumi will tell us.
have studied neutron generation from piezoelectric material flashed in these atmosphere. This phenomenon is so-called mechanical nuclear interaction. Only in the system of lithium niobate with D2 gas, the neutron emission was observed. This is the mechanism. The blushing of piezoelectric material, ionic charge appear on the blushing surface, caused by breaking of chemical bonds, accompanied with the generation of high electric field by piezoelectric effect. The charged particles are accelerated by the piezoelectric field and collide each other. Then diffusion occurs. This is our system. We measure the dependence of the excess value of the neutron emission on D2 gas pressure and excess neutron number per hour. In low pressure region, the excess neutron was not observed. While in the high pressure region, larger than 30 kilopascal, the excess neutron was apparently generated. Thank you.
I believe, unless we've inadvertently passed over someone who is present, that the last poster will be P79, nuclear products associated with the Planck's inflation effect, including commensurate to heat generation, calorimetry, and radiation. The authors are Bush, Legowski, and Miles, and I believe Dr. Miles will be the presenter.
This is work I'm presenting for Ben Bush. He's at the University of Texas. He used to be a postdoctoral student working with me. He's compiled his results with some of ours to show that the power versus helium atoms falls closer to 24 MeV per helium than it does to 4 MeV, suggesting that it's a DD reaction based on that. Earlier data translated was isoparabolic calorimetry. He is now using a high-performance Calvate calorimetry at the University of Texas. He's also interested in looking at neutron activation techniques for nuclear product analysis. This is not yet been done, but he's planning on doing it soon, using prompt gamma activation analysis, PGAA, neutron activation analysis, and AA. They're complementary methods. The PGAA analyzes short-lived neutron activation products, while NAA analyzes longer-lived neutron activation products. And so those studies are planned in the near future. And his summary is that nuclear products analysis has continued in the work that he's doing. And he has a new type of calorimetry, Calvate calorimetry. And they're expanding our efforts into looking at activation products in the cathode. And then finally, his conclusions. He believes this is the reaction, and they're planning on looking at side reactions where it produces radiation and neutron activation products in the cathode. And then the acknowledgments of various people here, including the funding is from the Electric Power Research Institute at Crescent, for his work at Crescent. Okay, thank you.
Okay, at this point, we'll
you find
terms of atoms per cubic centimeter per second, we're talking about something like 10 to the 16th. If you convert that to the roughly a number of MeV that would be released per atom formed, using an estimate of power production in this cell being about a half a watt. We quote a half a watt plus or minus 0.4 watts. The calorimetry is not very tight, so the number is uncertain, but the point would be it didn't produce a lot of power, and the number here is surprisingly low. This is because if you assume these are nuclear reactions, it's very easy to think you should get higher numbers. I'll come back to that issue in a moment. Let me jump over a minute to the difference in the isotope quantities measured versus natural abundance. So this is the difference in what we measure in SIMS compared to the natural abundance, the difference in percent. And again, I picked on, you can see there are many differences, and some of the low yield elements particularly have large differences. Some of the high yield ones have less. Copper and silver we're still picking on. The SIMS measurement on single beads gave something like 0.8% plus for copper 63 minus 0.8% copper 65. We worried that the SIMS could be very confusing because of the possibility of differential diffusion and other things, and we're only looking at very local spots. And so we've done this with neutron activation analysis, using 10 beads to get an average. It gives much higher percent, same direction of plus for copper 63 plus 3.6%, copper 65 minus fairly large uncertainties. There's an overlap. You should have plus and minus is equal, but when you do it this way, you get somewhat larger uncertainties and not exactly the same number. Silver 107 gives about plus 5% and minus 5% for 109 on SIMS. NAA has been done on it just recently, and we get about plus 4, minus 4 or something. Actually, it's much better percent agreement. So concluding, these results quite large, surprisingly large yield. Radiation emission surprisingly small. Purity issues, any purity source we can envision has been ruled out. Product rates, we're talking about tens of micrograms per 1,000 microspheres and so on. Isotope ratios deviate from natural. This requires more study though. I'll be showing some comparisons in a minute. The systematics showed reasonable agreement, other data. I'd and uranium. And of course, that produces a variety of elements, some of which are stable in their form, others are radioactive. I've been looking close at what type of comparison to make between the stable ones and what we see, but I don't want to comment on that here. I want to illustrate what seems to be necessary. For example, if you say we're going to have silica, zirconium, cadmium, I have lead here because you'll see it in later slides. Lead is a prevalent component in some of the later higher groups. You want ratios like this, we have different things. In order to produce all these elements, you almost have to have combinations of nickel proton reactions giving heavy elements, which then I would envision with fission, and these are typical fission channels, light, heavy products. Some are plus, some are minus. In some fashion, you need to balance these. You end up adding, subtracting energy releases, and you can get virtually a null energy output from all this. What I show here won't quite do it, but it illustrates the principle. What we need to do is end up getting a balance of the energy, the yield, and the deviation from natural abundance and all of this. And I've tried very hard, but this is about as far as I've gotten it with the model. All right, I have only a few more minutes, but it's important, I think, that I show you an additional run. We've concentrated on run number 8, which is nickel on plastic. Before doing that run, we've done runs where we have nickel plastic, excuse me, I'm sorry, nickel on plastic, but we have multi-layers, nickel plate, nickel. We have a run where we have this palladium nickel. This happens to have been put down by electroplating, give thick layers to contrast the others. We have one palladium on plastic. We put a nickel on glass and a nickel on plastic. Results from all these I'll show graphically. The most exhaustive run that we've done, which is fairly recent, was one that was, again, a nickel on plastic. It's like run number 8. This is number 18C. We've learned more. Jim Pavis did this in his laboratory rather than my doing it. I did the first run, number 8. This is done in what's called an ultra clean cell, where Jim had all plastic parts. The electrolyte was super clean, so it had less impurities in by an order of magnitude than what I showed you earlier with number 8. And surprisingly, with the cleaner cell, it showed up getting more products than the one that I showed you before. I'll superimpose on top of it. Here's the sort of identical run done a half a year earlier in my lab. They aren't too different, but the new one filled in some out here in this high weight group, and so on. I think the others know how to run cells better. Now, if you do, number of people run Patterson-like cells with nickel on glass and fail to produce heat. So we're very curious as to whether or not that shows up in these products. This happens to be the result of a nickel on glass run, and you can see this whole area has changed considerably, and there's a decrease in yield on this side too. If you go to the palladium on the first nickel runs I showed you. The electroplated thick one has all curves move down some and tend to accumulate in there, fewer out the far side. This is a comparison of that particular plating on plastic run to the work done by Dr. Zuno and colleagues at Hokkaido. Now they have completely different configuration as the thick plate, palladium, D2O, not light water, and so on. And their products, as I understand, are measured about a millimeter beneath the surface, and thin layer. It's almost like they have one of our thin films embedded a millimeter beneath the surface. But you'll see that the general trends of these four regions of the products are about the same. They produce copious gas, particularly xenon, which are not produced in our runs exactly. Our runs with thin films probably allow the gases to escape, whereas with theirs forming this beneath the surface, it's trapped. Incidentally, what we did was normalize the copper from their runs to our absolute values. We didn't have an absolute value for their yields. If you take all of our runs and plot them on one graph, you get something like this. This very distinct pumping. So if you would feel that this pattern is quite a frequent in these types of situations. If you take all the runs and plot the deviations of natural abundance, one gets quite a scatter graph. Quite a scatter graph, but there are many differences that have to be tracked. So let me conclude saying that these large yields appear possible in thin films represent a way of quantizing the experiment, because it is possible to do fairly accurate mass balances on the products to find out if one is actually producing more than have been there to begin with as impurities. And there are many unexpected features which I've stressed. The systematics, though, seem to fit with the growing body of observations and others. I haven't had a chance to compare with some of the other experiments. I think if you look at people who are reporting this type of thing, you'll see the same characteristics increasingly. More work is needed, and we have much work planned for ourselves, such as trying to establish a connection to excess power, if there is one. One needs to look at the reaction rate variation in time, and also position, study, in our case, products that might be gases that are escaping, so on and so forth. So I feel this is just the beginning in what appears to be an entirely new area of this cold fusion work. Must have a connection with the traditional quantum splasm type of experiments, but yet the features are so strikingly different that it represents a different field within which to explore. Thank you.
Mr. Kumari. Now this paper is open for discussion. So shall you give us some, please?
Yeah.
Yes.
Did you look for these elements in the electrolyte at all?
Did I what?
Did you look for all these elements in the electrolyte?
We always look for 9 elements, which are the ones I marked as high yield, which included copper, silver, iron, zinc, cadmium, and so on. So all the high yield elements, which since high yield I feel important, we always measure with neutron activation analysis before and after the run in electrolyte. So I can say without question that for those 9, there's not anywhere near enough in electrolyte if it all went into these to represent what we see.
Another question. Did you have a statistical analysis of the distribution in different peaks so that you can integrate and say so many milligrams is produced in the whole cell? Percentage of the peaks that were analyzed as compared to the total number which participated in the experiment.
In the nickel one, which we've been looking at, there are 1,000 beads, and we've run 4 different independent neutron activation analysis on 10 beads that are taken from sort of the top, 10 are taken from the next layer down, 10 from the next layer, and 10. So we've sampled something like 40 beads out of 1,000. And because we've done it in layers, we feel that it's fairly representative.
Let's move to the next question.
This appears to be not fusion, maybe spontaneous fission, or like maybe cold fusion is normal. Maybe we should call like a ultra low energy nuclear reaction.
I call it RIPEX.
Right. One question I have is today lunch hour, Bill Collins, I looked up all possible reactions because he has a program to do that. And is there a possibility of platinum being involved? That is, somehow platinum interact with proton, somehow overcoming proton barrier. And that can give like silver and germanium, as well as if you invoke oxygen and carbon in plastic, then you can cover most of the product you have seen without invoking negative Q values.